Okay, so welcome to the next session. As we just indicated towards the end of last session, we had three important steps that make the meltdown attack. One is that every process has a address space in which its own data, code and stack are served, but then there is a space allocated for the kernel. So this is true for every process, and what happens is the space which the kernel space, the operating system space, is not exclusive for every process. So two processes can basically share the same kernel space. So as process P1, if I write some secret into the kernel which is stored in the kernel, another process P2 will have, if it can have access to the kernel space, then it can read my secret. So by this a process P1's secret can leak to P2. So that is the first part, and the second part is there is an hardware out of order execution. We will also deal with that in some detail. I have already dealt with it in IS2, the information security 2 course, but I will give a brief outline of that, and that is also exploited. And then there is a microarchitecture level hack that is done where the cache is basically utilized to leak information. So these three steps are forget that this is it's a security vulnerability which is causing a lot of concern, but from the other angle it's a very brilliant way of breaking into the system. So let us now deal each of this in quick succession. We will just see what is in store for each. Now first one, let us talk about the address space basics. I have just talked about it in the previous sessions in this course itself, but I will just summarize that very quickly, and whatever I am summarizing has been part of the information security 2 course and the information security 3 course. So if you find something that you are not able to quickly follow, I also suggest that you go back to those videos and have a look at it to have a much broader deep understanding of the concepts that I am going to cover in this part. So there is a need for a process P1 to interact with the operating system, whether it wants to print some value, it wants to take some memory like malloc, etc. So or it wants to accept a value from a keyboard. For everything there is a need for the operating system, for the process to basically look into the operating system for help. And when there is when the operating system executes a system call, right, when the application executes a system call, or there is an interrupt, the operating system, the interrupt service routine, system call is also like an interrupt to the operating system. So your system calls and the interrupt service routines are also part of the operating system. So there is lot of interaction between the application program and the operating system. So let us now go and look at very clearly. So when a process starts executing, essentially from the process point of view, there is a memory space which is 4GB. Let us take it's a 32-bit architecture, so 4GB address space. So if I am a process P1, I am given a 4GB address space. Similarly, P2, another process P2, it's also given 4GB address space, right? And then OS also will get a 4GB address space, but then the actual RAM can be 1GB, right? So this is the concept of virtual memory. So every process will get the whole 4GB, and then but the actual thing would be only 1GB. Actual memory can be 1GB, right? And this is how paging works. So paging takes care of maintaining these individual address space for processes. OS is also a process. Please understand that OS is also a program in execution, it's also a process. Now let us see what is going to happen. Suppose this is the stage where I say P1, I can't give the entire 4GB for P1, so I will give some space for P1, I will give some space for P2, I will give some space for OS. Okay. So this entire 4GB address space will be shared and used. Shared in the sense that some part it can be it is exclusive. So let us say I do not want to share a same virtual address within 3 processes. So suppose P1 requires some amount of space, so P1 will have its space. So in the corresponding page table, those pages alone will be enabled. in the corresponding page table of P2 those pages will be enabled, in the corresponding page table of OS those pages will be enabled, right. So, if you have understood paging you will understand what I am talking here. So, if for example P1 is say 16 KB, each page is 4 KB, so I will have 4 pages for P1 and I will have say let this be 32 KB, I will have 8 pages for P2, let the OS be some large one, then I can have 20 pages, 25 pages for OS. Let us just talk. But then I will ensure that the pages are not the same page is not shared. So, that means with respect to the virtual address space each person has got a separate isolated memory. Now, if that is the case, now let us just take P1 and the OS, the P1 and OS. So, P1 will not have any access to the OS pages, right. So, because in the P1 space table there will be no entry corresponding to where the OS pages are, right. The OS pages also will be in that 4 GB address space, P1 pages also will be in the 4 GB address space, but the entries for P1 in the P1 space table will correspond to only those pages that are allocated to P1, the other pages it can never access, and so the OS cannot be accessed by P1. So, this is an ideal scenario. If that is a scenario, now let us take a very simple example like a keyboard, you press some say some character in the keyboard, where it will go? It will go and basically gets saved in the OS address space. So, in some page corresponding to the OS there will be a buffer in which this whatever character you have entered will go and stay there. Now, who is asking for that character? I am an application program, I am doing a scanf. So, I need that value, I as a process. So, P1 needs that value, but that value when somebody presses the keyboard then there is an interrupt generated, and what will that interrupt do? There will be interrupt service routine, that will be actually the keyboard controller or whatever, and then the data that is typed actually comes and stays in the OS address space. So, then finally the data is needed by the process P1. So, we have to copy it exclusively from the OS address space into the user address space or the process address space, and then P1 has to read. So, there is an extra memory copy that needs to happen, and it needs to happen for every character that you are entering, and that thing is actually from one page table to another page table. Since this page table will not have any entry about the OS pages, and your value is actually stored in some place which P1 cannot see, and so now OS has to transfer it back there. So, this extra copy is needed, and all this because P1 does not have the page table for P1 does not have an entry for the operating system, right. So, this will really have a big performance hit, and the solution which the different advisories are basically suggesting to handle this meltdown attack is very close to this, saying that you have a separate address space and then you copy from that to this. It is very close to it, not exactly, but we will say what exactly the solution that they are presenting in the later set, but this is very close to this. So, so essentially to sum up this slide, if the process P1, so every process has its own page table that we have seen in the earlier class, earlier session, where we had this task state segment, there is a CR3 entry there, the CR3 entry points to the start of a page table. So, every process including the OS, which is also a process, can have a page table of its own, and in the page table of process P1 I have entries only corresponding to process P1's data code and stack. In the OS I cannot see the OS page. If that is the scenario as we are seeing here, which is very ideal, a meltdown cannot happen in this type of a context, then every for example a simple thing like a keyboard IO keyboard input should cross at least 2 stages before it reaches the application, and that is going to have a serious performance hit. So, this is a costly operation as you see in the screen, right. Now, let us so what has happened is today what they have done is to optimize this. That is the reason we have been saying the process in the page table for the each of the process there is an OS page is also loaded there. So, I need not go to a separate page table, look for where the OS is and then collect data and then come back to this page table and then store it in some location. The page table of process P1 has something for the process which is on the top, and whatever is shaded in the down is completely this OS. And when I switch to process P2, again the process P2 pages will be there, and then the same OS pages, the same link will be there. So, the same page table can be and the same page entries are replicated here. So, that means P1 and P2 will share the same set of OS pages. So, as you see here on the screen, the entries for the OS, the last 3 entries in the P1 page table will be the same as the last 3 entries in the P2 state table. Essentially they are pointing to the same page. So, though I have 2 different page tables, one for P1 and another for P2, the pages that they use for the kernel, the pages that they use for themselves, they are isolated, but the pages that they use for the kernel are basically shared. Now, that means if P2 writes something into the kernel, P1's page table will have a pointer to access that, right. So, if I start accessing it, whether I will get it or not is another question, but there is an access through the page table of P1. I can go and access what P2 has written into the kernel, right. Now, so far what we all of us believed was that as a process I cannot go and access the OS region. P1 cannot reach the OS region, similarly P2 cannot, and that is precisely what Meltdown says that it is now possible, and that we will see how it is going to be possible and how the information can be leaked. Okay. So, so this is the scenario, but now every operating system does this type of a thing because of what? Because of performance reasons, right. So, if I had isolated OS is isolated from P1 and P2 address spaces, then IO becomes extremely complex. Just to get rid of this, this now becomes a safe and sound way to share data between OS and P1 as of now, but with Meltdown that safeness and safety and soundness has literally melted out. Okay. Now, let us see how that is going to happen. Now, in this virtual address space, if I have a keyboard interrupt, basically the data now goes and stores in the OS address space, but that OS address space is accessible by both P1 and P2. So, now the copy, there is no extra copy needed across different page tables. It is not just copying from one memory location to another memory location. Now, this whole memory access is governed by paging, and so there is one page table and there is another page table. From one page table entry to another page table entry, I have to do a copy. So, that really makes the whole thing much complex. So far as I just summarized now, can P1 access the OS space today? As of now, no. Why? So, the way we have believed so far is that no, it cannot access. Why? Because this again I have explained in much detail in the IS2 course. The hardware allows 2 modes, user mode and supervisor mode. In actual Intel we have 4 privilege levels. Privilege level 0 is the supervisor mode, the highest powerful, PL1, PL2, PL3, right. So, there is an hardware bit that indicates the mode, and this is called a supervisor bit. You can see this in all your descriptor tables, etc. Right. The supervisor mode will have extra permission compared to user mode. For example, it can execute privileged instructions. We have seen what are privileged instructions in the information security 2 course, right. So, we can keep executing privileged instructions and so forth. Now, what is the step involved in actually accessing the OS page as a process? P1 actually tries to access the OS page in its virtual address space. Hardware checks if the page can be accessed in user mode. Now, it cannot be. So, essentially an exception is raised, and the exception handler will take care of whatever P1 wants. And this is precisely what we also call as a system call. So, malloc, what I need some memory. What I mean I need memory. So, the operating system, so when you are executing program, suddenly you read lot of memory, so you ask for this memory allocate. Now, the operating system basically maintains a list of free memories, right. So, when as a process I need memory, I just execute the command malloc, which essentially means I have to go to that list, find out some memory chunk. It will have a list of free memories, means it will have a list of chunks of, oh, there at address 1000 there is some 512 bytes of memory free, at address 2000 there is some 3 MB of memory starting from 2000 free, like that it will have the list. So I need to go to that list and basically get the get one chunk allocated for me. Now the free list will say okay, it will delete that part of the memory and give it to him, give it to the, meaning that will be used by the process. So I have to go and access the free list. So when I say malloc as a user process, I want to access the free list, which cannot happen because the free list can be accessed only in supervisor mode. So immediately there will be an exception that will be raised. When the exception is raised, again in IS2 I have covered that, an interrupt service routine will start executing, and an interrupt service routine will find okay, this is, he is trying to access this and this is a system call, and so the operating system will allocate the memory. It will, operating system will go and look at the free list, it will find out which chunk of memory I am asking for, say 100 bytes, which 100 bytes I can give it to him, and then it will remove from the free list and put it in the occupied list and then release back, and so I can start using that 100 bytes. So this is how the whole thing basically happens. So that is also another reason why the kernel has to be shared. Like I ask for some free memory, that I have asked for that free memory and that is allocated to me should be known to the other process also. If it is not known to the other process, say let us say there is a separate OS image for both of us, I ask for some memory, then that memory the OS image has given me, it should be known to the other image also, right. If it is not transmitted to the other image, then there will be no consistency. Two processes can get the same image and that is enough for all security vulnerability to end of story for that. Okay. So essentially there are a lot of things the OS needs to carry which are global in nature, like importantly the free list of memory, how much memory to whom I have allocated, and so that I do not reallocate the same memory to other fellow. So essentially going back to this slide, the pages where the pages corresponding to the OS in the P1 space table that you see on the extreme left and the P2 space table, those entries will point to the same OS pages, and the necessity is that P1 and P2, P1 if there is, say for example there is a memory allocation done for P1, it is very important for P2 to note, because when P2 asks for memory then the same page should not be allocated, so that it will go and corrupt that data and it will also not execute correctly. So this is also precisely a reason why every OS should have an access to the operating system, every process should have an access to the operating system. Now this type of an address space isolation, where there is an OS address space and then the process space thing, every user process is given access to a part of the RAM for its execution, that is the user space, and the user process cannot access the physical address allocated to another process including kernel. The kernel has access to physical address space of all processes, that is kernel will have access to all the entire RAM, but the vice versa is not true. From this, what is going to be meltdown? Meltdown is going to melt this particular, shake this particular isolation guarantee. So what it says is somehow we will enable the PIs, the processors, to read the OS mapped page from PI's own page table, right, and that is what is achieved here. And the moment I can go and access my same page table, if I am able to access the kernel page, then what will happen? Obviously the kernel is shared, some other process would have written something into that kernel which I can basically leak and get it out. So this is the entire concept of the meltdown. We will now see out of order in the next session. Thank you.